Welcome to this explainer. I am so thrilled you're here today because, well, we are going to pop the hood on some truly incredible mathematical machinery. We're talking about advanced simplex algorithms. Now, if you're already familiar with standard linear programming, you know it's a brilliant way to find optimal solutions. Things like maximizing profit or minimizing cost. But there is a catch. Standard models usually rely on a really convenient starting point, which is the origin. Essentially, you're producing 0 units of everything. But what happens when we're dealing with complex, real-world models where that usual starting rule just doesn't apply? Well, today we're going to explore exactly how we handle these tough logistical roadblocks.
Okay, let's map out our logical flow for today. We'll start with 1, the starting point problem. Then we'll look at a clever workaround in 2, inventing artificial variables. From there, we'll explore 2 heavyweight algorithmic solutions, 3, the big M method, and 4, the two-phase method. And finally, we'll wrap the whole thing up with 5, choosing the right approach.
Section 1, the starting point problem. So what actually happens when producing 0 just isn't an option? Right, so in standard linear programming, constraints are usually less than or equal to. Think about it like this. You've got a limited amount of factory hours or raw materials, so producing 0 units is a perfectly valid, even if it's totally unprofitable, starting point. And the math absolutely loves this. Setting all your decision variables to 0 immediately gives you an initial, basic, feasible solution. But here is the massive problem. What happens when your constraints demand an exact amount, using an equal sign? Or what if they dictate a strict minimum requirement using a greater than or equal to sign? Suddenly, starting at the origin, producing 0, it completely breaks down. It literally violates the rules of the model. You can't start at 0 if the equation explicitly demands you produce at least 10. So we're left without a starting line. And without a starting line, the simplex algorithm just cannot run.
Section 2, inventing artificial variables. This is where we look at how to create a starting line basically out of thin air.
To bypass our starting point problem, we literally have to invent a brand new piece of the puzzle. Enter the artificial variable. By definition, this is a temporary, non-negative dummy variable that we introduce into a complex constraint for one reason only, to create an initial basic feasible solution. I actually like to think of this as a phantom number. We inject it into our rigid equations simply to force a temporary starting line into existence. It has absolutely no physical meaning in the real world. It doesn't represent actual products on a shelf or hours on a clock. But mathematically, it's a lifesaver. It allows the simplex method to boot up and actually begin its work. Let's look at these two concepts side by side. On one side, we have the real problem. This is our actual real-world model, with its rigid constraints and absolutely no obvious starting point. On the other side, we have the artificial problem. Now, this is the exact same model, but we've injected it with our temporary dummy variables. We essentially swap out a completely impossible puzzle for a slightly modified, solvable one. We've basically built a bridge, but we have to remember this bridge is entirely artificial. We can't stay on it forever. Now, what's really fascinating here is how the math actually maps these modifications out. Look closely at this equation. We have a real constraint. 3x1 plus 2x2 equals 18. If x1 and x2 are 0, well, 0 obviously does not equal 18. The math is stuck. But watch what happens when we add the artificial variable, which is represented here as x bar 5, directly into the equation. We get a brand new equation. 3x1 plus 2x2 plus x bar 5 equals 18. Now, if x1 and x2 are 0, x bar 5 simply takes on the value of 18. Boom! Just like that, we have our initial basic feasible solution. The simplex algorithm can finally start its iterations.
Section 3, the big M method. How do we force these phantom variables back to 0?
Okay, so to remove this artificial variable before it ruins our final answer, we use an ingenious concept called the big M method. I want you to imagine M as an overwhelming astronomical number. Think of 999 million or even infinity. Conceptually, M represents a massive, unforgiving penalty. Think of it like a gargantuan tax that we assign exclusively to our artificial variables.
The absolutely crucial point here is that by adding this massive penalty to the objective function, we completely change the mathematical stakes. If we're trying to maximize profit, we subtract m times the artificial variable. If we're trying to minimize cost, we add m times the artificial variable. Because the penalty is just so incredibly severe, the simplex algorithm's natural mathematical drive to optimize efficiency is going to brutally crush that fake variable down to 0 as fast as humanly or computationally possible. The algorithm basically realizes, hey, as long as this artificial variable exists, this massive penalty is absolutely destroying our score. So it forces the dummy variable out of the solution entirely, leaving only the real variables behind.
And this visually brilliant graph illustrates that entire journey. Notice the dark gray feasible region here? That represents the artificial problem we created. It's exploring mathematical spaces that aren't actually possible in the real world. But as it iterates, it uses that crushing M penalty to navigate its way out of the artificial zone and push right down onto the boundary of the real problem's feasible region, which is that solid dark line you see right there. Once it hits that real boundary, the artificial variables are completely zeroed out, and it just continues searching along the real constraints until it finds the true optimal point. I mean, it is a mathematical masterpiece.
Section 4, the two-phase method, a more streamlined alternative to Big M. So here is the real-world limitation of the Big M method. While you or I can write the letter M on a chalkboard and just pretend it means infinity, software programs, well, they have to use actual tangible numbers in their code. If a computer tries to process a massive theoretical penalty number, let's say 1 billion, right alongside tiny decimal coefficients like 0.4 or 0.5, it can cause severe numerical instability. The computer basically suffers from rounding errors, and those small but super vital decimals get completely lost in the sheer scale of M. The software just gets confused. Because of this very real limitation, we need a more elegant polish for actual computational use. And this is exactly where the two-phase method steps in. It's a beautifully streamlined alternative that completely removes that dangerous M from the equation. Instead of trying to do everything all at once, it separates the heavy lifting into 2 highly focused sequential steps. Phase 1 has only one single job: minimize the artificial variables to 0. Actually, scratch that. It's more like a search and destroy mission for fake variables. It doesn't care about your real profit or your real costs. It just wants to find a legitimate starting point. Once it achieves that, Phase 2 takes over. Phase 2 drops the fake variables entirely and optimizes your real objective function using the totally valid starting point it just found in Phase 1.
Let's see how this actually builds out in the equations, using a radiation therapy example. You can see the clear separation right here. Look at the Phase 1 problem. The objective is simply to minimize z equals x bar 4 plus x bar 6. Those are our artificial variables. We are temporarily replacing our real goal with the strict mission to crush the fake variables to 0. Once that's solved, boom, we've secured our safe starting point. Then, Phase 2 begins. It brings back our actual real-world goal, minimizing z equals 0.4x1 plus 0.5x2, but it does it without the burden of those artificial variables confusing the computer.
Section 5, choosing the right approach. Let's compare these two methods. As we look at the algebraic differences side by side, the core distinction becomes crystal clear, doesn't it? In column 1, the Big M method is trying to juggle everything in one massive equation, combining the real variables and the heavily penalized artificial variables all at once. In column 2, the two-phase method splits the objective. Phase 1 focuses purely on the artificial, and Phase 2 focuses purely on the real. Now, what's really fascinating is that mathematically speaking, because these virtual equivalencies are so incredibly strong, both methods generally have the exact same sequence of basic feasible solutions. They take roughly the same path to get to the end. But practically, in the real world, the two-phase method safely drops that dangerous M multiplier entirely, completely sidestepping the numerical instability that plagues modern computer software.
And that brings us to the end of our explainer today. We've gone from being completely stuck without a starting point to inventing phantom variables, punishing them with massive penalties, and eventually streamlining the whole process for modern computers. It's just incredible to think about. You know, when an airline schedules its thousands of daily flights or a giant logistics company routes millions of packages perfectly to minimize their costs, it isn't magic. It is advanced Simplex algorithms, exactly like the ones we've explored today, actively overcoming strict constraints and working relentlessly toward the optimal solution. So I'll leave you with this final thought. How are these hidden mathematical algorithms running behind the scenes right now to optimize the supply chains, the healthcare systems, and the software you rely on every single day? Keep wondering, keep learning, and I'll catch you on the next explainer.